I would like to also present co-chair of this session, Sang-Mook Lee, who is the chair of the local organizing committee and who is actually the very much should be thanked for their in general organizing of this conference. I can't close something, sorry. I don't see you. You see my screen without any other things because it's in my screen. There are a lot of other stuff. Yeah, hopefully you can't. I can't delete them.
We see the full screen presentation.
Full screen presentation. Excellent. Yeah. Thank you for attending the keynote lecture. And the Vladimir Keilis-Borok medal has been established by the IUGG Bureau in 2021 to recognize the middle career scientists who made important contribution to the field of mathematical geophysics. And actually the aim of the medal is to honor the legacy of Professor Keilis-Borok in promoting transformative scientific advancement and the selfish leadership. I would like to mention that Professor Keilis-Borok was a founder of the Commission of Mathematical Geophysics and was a president of IUGG from 87 to 1991. IUGG has awarded the 2022 inaugural Vladimir Keilis-Borok medal to Frederick Simons for his outstanding contributions to mathematical geophysics and development of cutting-edge mathematical methods in geoscience data analysis. First of all, congratulations to Frederick. Frederick, unfortunately, we are on site. We cannot award you by this crystal medal. And this is a medal which will be delivered to you any way which you prefer, or in Berlin if you will attend the IUGG General Assembly or some other way. And at the same time, it is my pleasure really to introduce Professor Simons for this lecture. Frederick received his master diploma from the Catholic University Leuven in Belgium, and the master diploma was in geology, and he got his PhD degree from the MIT in geophysics. He lectured in the University College London and has been visiting scientist and professor at many European academic institutions, including the University of Cambridge, ETH Zurich, and the Institut de Physique du Globe de Paris, before he moved to Princeton. Frederick received a number of awards, including the US National Science Foundation Career Award, Distinguished Lecture Award of the Seismological Society of America, and Charles Lagrange Prize of Belgian Academy of Sciences, just a few to mention. His research is related to solid earth geophysics. He studied physical properties of the terrestrial lithosphere, focusing on particular on the elastic and thermomechanical properties of the continents. He used the seismic tomography and cross-spectral analysis of to study the provenance of gravity, and topography. Frederick developed mathematical methods for the localized analysis of scalar and vectoral fields on the sphere for satellite geodesy, geomagnetism, or even to cosmology. Designed a wavelength-based signal processing methods for global and exploration seismology, and developed oceanic instrumentation to close the seismic coverage gap over the Earth's oceans. Well, I think it is the time to invite Frederick to deliver the medal lecture. Frederick, now I will stop sharing my screen. You are invited to share your screen, and the stream is yours.
Thank you, Alik, and thank you, Sang-Mook, very, very much. This is the talk. And I think you're going to see this full screen. And I should make it even bigger. I don't know why it's not even fuller. I should put it in presentation mode. Actually, you know what? I'll open a different. I think this is better. Please let me know if you cannot see it, because I cannot see your faces. I should tell you that I'm actually in Korea, which is a great pleasure and a great honor. So I didn't have to get up at 2 in the morning to do this. That's obviously very nice. I think I should just go right to it, because I do want to cover quite a bit of ground here. Thank you very much again for giving me this honor of receiving this medal. The only downside is it looks like I cannot wear it, given how big it is. And also it sort of says that, you know, if you're middle career, I don't know, that means maybe the end is near. But I want to take this opportunity to reflect on about a decade of a particular theme in my research. And I made this talk here to try to summarize quite a number of papers, and I hope I'll do a good job. So it's going to be about linear inverse problems and about quadratic spectral estimators, specifically related to planetary potential field data that are collected typically by satellites at a large altitude. And so that type of data is what we want to use to infer properties of our lithosphere and planetary lithospheres at a different depth, namely at the surface, or conversely, if we're collecting data on the surface, that we want to go deeper and look at the interior of the Earth. Of my many collaborators, I chose Alain Plattner, who was a postdoc with me for several years and is now a professor at the University of Alabama, to highlight some of his vital contributions to all of this, which I'll be presenting. And then in no particular order, or rather I'll read them in a particular order. Tony Dahlen, who was my postdoc advisor, and it's fair to say that without him, I would have certainly started this work, but I wouldn't have been able to finish it, because many of the contributions show his vital input to it. And that's the same for Marc Wieczorek in Paris, who's been my longtime collaborator and colleague and friend. And then there's been a variety of other collaborators, students, Jessica Hawthorne early on, Kieran Began, and then postdocs, Kevin Lewis and Chris Herrig, and then some more at-large collaborators like Xinshan Han and Volker Michel. So if anything, this of course illustrates that we all work together. One never should claim any credit for anything on one's own. So if you want to start with one sentence, it would be that mathematical functions cannot be band limited and space limited or time limited at the same time. This is a truth that goes back to Norbert Wiener and Paley in over 50 years ago, maybe even longer than that. So what we can, however, do is we can try to find a set of band limited functions and squeeze them into a spatial area. Or conversely, we can try to find a set of space-limited functions and squeeze them into a region of spectral space. And by squeezing, I mean optimized concentration according to a criterion that I'll show you. So collectively, all of these approaches yield a new set of functions, which we've been calling Slepian functions in honor of a mathematician named David Slepian. And I'll be telling you how we're using them for all sorts of geophysical analysis problems. So for spectral analysis, which will be these quadratic estimators, or for approximation or inversion problems, which will lead to these linear problems. When I mean space, I mean regions of space, like on a sphere, like R1 and R2, two continents, or a spherical cap, like a detector or a lens that you move around, or like a double cap, if you want to study more things more further afield, like in cosmology, but also in typical satellite coverage where there are polar gaps and so on. So the region of space here can be very general. But I'll begin with the real fundamentals, and possibly with something that you all have learned, and that is the following. If we have a band limited time function g, which, because it's band limited, is entirely characterized by a Fourier transform that doesn't go to infinity left and right, but that goes from negative w to w, and knowing that you cannot therefore have a time limited other function, these Slepian functions are trying to squeeze, as I was just saying, this type of function into a finite time domain. And that's this lambda here, where we're trying to optimize the ratio of how much energy goes within the time limit, divided and normalized by the entire real line. So Bailey-Wiener theorem tells you that you cannot ever do this. So these equalities are strict here. The eigenvalues, or these concentration ratios, are strict, but we can do very well, as I'll show you. Now, if you do a little bit of derivation, then you find through Rayleigh's principle that these unknown functions, which from now on I'll denote in this magenta color here, these g functions, are going to be eigenfunctions of a Fredholm integral equation with a kernel, like all the kernels that I'll be showing you, which will be in this blue color here. And so this is a sort of a sinc kernel that you probably all learn about in signal processing. What the next step is that you can then find these magenta functions g here, and they have a whole set of nice properties. So in the two-dimensional plane, this is a problem that Slepian also tackled, although not in complete generality. It's the same thing. You're beginning by saying that there shall be a band-limited function, which, in other words, doesn't live on the entire R2, but rather in some spectral domain called kappa or k. And you're going to try to squeeze it. And now you have a 2D integral over an area R with of measure A. And they are again eigenfunctions of a very similar equation. And so once again here, the unknown functions, the solutions, are the Slepian functions, which are in magenta. They're called G, but now of space. And they're going to be eigenfunctions with eigenvalue lambda of this other operator, which you get through after a minimal derivation here. And then finally, and this is where we really started back in the day with Mark Wieczorek in 2005, we just wanted to do that sort of thing on the surface of a unit sphere to do planetary science. And so again, beginning by a partial Fourier expansion, but now because it's on the surface of a sphere, these are spherical harmonic functions. If they're limited to big L, so that it's not to infinity, we're going to try to squeeze them in a surface integral over the surface of the sphere, omega. And once again, they are eigenfunctions of an integral equation. And here the blue is their kernel. P sub L is the classical Legendre function that you also need in this context. So I'll begin by some examples here. If you have a spherical cap or a circle in the plane, these functions, when you compute them, and I haven't told you how to, they are just beautiful. And I think ultimately there is a appeal to it that motivates us to do this sort of work here. The very first one is sort of a dome-like function. The second one is a bilobate function, then rotated. And so they have all these beautiful symmetries. These are spherical functions here, so they sort of fall apart into their zonal and tesserail orders. And from left to right, as the read in English text, they're diminishing in concentration value. So you're not seeing it here because I'm not listing nearly all of them. But if you keep going, they will start leaking out of this area of interest, which is this region R of area A, which is denoted by the dashed line here. But I told you the area R doesn't have to be spherically symmetric or cylindrically or circularly symmetric. It can in fact be anything. And that's where most of our applications lie. So I'll show you Greenland. If you try to squeeze a band-limited spherical harmonic expansion into the domain of Greenland plus a small buffer here, then you're also going to get a whole set of functions with a diminishing concentration here. This lambda is almost 1, it's not exactly 1. And then it goes down to 99 and 99 and 95 and 93%. And there's 361 in this particular example. And the worst ones are totally outside of Greenland, but all these very good ones, all the early ones, are very well concentrated inside of Greenland. So I'll return to this example because I'll be working with them. But again, you're seeing, so the symmetry is of course a little bit broken because Greenland isn't a circular cap, but you still see that the first function has sort of a nice symmetry, and then it's broken down in 2 and then 3 and then further pieces. Ultimately, these functions cover the entire area. So what I'd like to put together is something that when you have, as we did, worked with 1D and 2D spherical and 2D circular, 2D spherical, 2D Cartesian and 2D spherical function, then you realize that these blue kernels, these kernels of the integral equations here in this blue color, they're all of the same kind. I've rewritten the first one, which was a sinc, as a band-limited, as a spectrally band-limited spatial delta function. The second one is the same form as I showed you earlier. It's a spectrally band-limited spatial delta function, because if you replace k by infinity, then you'd have a delta function. And on the sphere, I've rewritten that Legendre function as an order sum over 2 spherical harmonics. So it's all the same thing. 10, 11, and 12 is the unifying framework for all these Slepian functions. They are eigenfunctions of this integral equation, and in whichever dimension, those kernels are spectrally band-limited spatial delta functions. And something that's also very important is that if you speak this language of the integral equations, then you wonder what is the trace of this operator. And the trace of the operator is the area in the combined space of time bandwidth or space bandwidth that these functions are able to live. So on the real line, the time bandwidth product, TW here, comes out as that's really where these functions, that's the type of area in information space that these functions occupy. Similarly, in 2D, it's k squared a over 4 pi, and you chose this other k here because I showed the example of a circular region where k is now the radius of that kappa. And on the sphere, well, the entire dimension of spherical harmonics to degree L is given by L+1 squared terms. That's all the orders and all the degrees. And that's the spectral component of the space bandwidth product. And then A is again the area of the spatial region. So these Slepian functions in whichever dimension or whichever geometry are bases. They're bases for band-limited geophysical processes anywhere. And that's not just on the domain for which they're constructed, but they're also continuing to be bases for the entire sphere. And that's a very important thing that implies that they are doubly orthogonal. You could use them on your region, you could use them on the entire domain, and you have the benefits of orthogonality in both these cases. And so that trace is the space bandwidth joint area that Shannon, the father of information theory, that's sort of an area that we associate his name with. And then if you remember that the trace of any operator, and if we can write it as a matrix operator, that's the sum of the eigenvalues of this matrix, then we're going to start calling this dimensionality, the letter M. So I'm just going to switch to the sphere and show you how we actually calculate them. We don't actually usually integrate in space and do this kernel, even though originally we did, but it's much easier to calculate these functions in the spectral domain. And all you have to do is find their spherical harmonic expansion coefficients. So again, that's the magenta G, but now is GLM, for that'll be the partial expansion. Well, it's a complete expansion, but only to an upper degree L. And there are again eigenfunctions, but now of this red kernel, and that red kernel is just all the interaction terms of different spherical harmonics when they are cross-multiplied and only integrated over the region R. So that's sort of a gram matrix, if you will. And so D now becomes a matrix, and it has elements DLM and LM prime, and that's exactly what this is here. And that trace of this thing is again the same thing. It's the time bandwidth product. And you want to see that, of course, if you have a small area compared to 4 pi, the area of the entire unisphere, that if you're trying to find these functions, that this number is going to play an important role because it shows you the dimension of where these functions fit. And you can tell, of course, that this area over 4 pi is much smaller than the complete set. So the smaller the area, the fewer functions you will need to do any of the problems that I'll talk about, approximation problems, linear problems, and so on. But the real trouble is that many of the eigenvalues of D are very, very small. That's troublesome to calculate, and that's also very troublesome to invert. Now that's a trouble, but it's also a benefit, as I'll show you, because then few functions will do most of the heavy lifting, but I want to point it out here. And then finally, just keep remembering that the spatial region, even though many of my examples are spherically symmetric, the region R can be anything. Greenland, Africa, you name it. So here are some looks of these eigenvalues. So this is for a spherical cap for 2 different spherical harmonic degrees on the left and on the right. And the key realization of all of this framework is that these eigenvalues are, while never 1 and never 0, there are n of them that are nearly 1 and the complement that are nearly 0. And the transition region is something that has an ultimately a narrow band. So the sum of all the eigenvalues, because it's mostly 1s and mostly 0s, is the number of useful functions that you need. And so I'm indicating that here, the sum of these eigenvalues, 24 or 42 in this case for 2 different caps, splits this thing into about half. And the sum, in other words, is almost their number, the number of interest. Africa, Greenland, North America, all of these have similar patterns here. These are for different spherical harmonic bandwidths. Take a look at the bottom right. So depending on the area of the continent, they are more or less, more or fewer of them. And so they all, however, have this characteristic decay. And I'm not showing the hundreds of them that are out to, the number marked on the bottom right here, because they are all ever closer to nearly 0. So I'm going to say one more thing about the computation, and that is related to the commutation operator. If you read the papers of Slepian et al., for a long while, they had trouble calculating these functions using these spatial integrations that they started out with. And that is because, again, they're somewhat hairy to calculate. But the big breakthrough that made Slepian famous ultimately is that he realized that while doing this proper problem exactly, if you have symmetry, then you can appeal to a completely different framework of differential operators that turn out to commute with these other operators, and you can calculate their common eigenfunctions at different eigenvalues much, much, much more conveniently. And so that's been described as the lucky accident of Slepian and the magic of commutation by Grunbaum. And so that's the last I'll say about it, is that if you're actually doing this on regularly symmetric regions, that any of these computations can be done almost by hand in the blink of an eye. And that's why in one dimensions, they have become very popular for spectral analysis, as I'll show you, but it's really because they're so easy to calculate. They're very well-defined functions, very well-concentrated band-limited functions, and their calculation is literally a piece of cake. So that same thing applies in 2D Cartesian and in 2D spherical, and even vector and tensor cases. Of course, it gets a little bit more complicated to find these operators. But if you're ever tempted to try something Slepian-esque, then try it on a symmetric region, and you'll see how childishly easy the computation of them is. So if I summarize that, right, I begin by saying the truth that, well, you take a basis for a surface of a sphere, here, spherical harmonics, and what it means is that their interactions here, their co-multiplication integrated over the entire sphere, is a set of delta functions. That's what it means to be an orthogonal set on a complete domain. But if you have a domain of interest like Greenland or Africa, that partial integration isn't a delta function, but it's rather that operator that we talk about, D. And that's really all there is to it. The eigenfunctions of this operator D, or this matrix D in this case, are those magenta functions G, and they're now a basis for all sorts of things that you need. They're doubly orthogonal both on the region of interest where their orthogonality product is lambda, and also still on omega where their orthogonal product is 1. And then that special number n, the sum of the eigenvalues, the dimension of that space, that's what we're starting to call the Shannon number, which is a space bandwidth product. And that's the effective dimension. So applications, I have 5. One of them is literally just approximating a function on a small domain. This relies on the following. If you have a band-limited function and it is completely expanded by it's a signal S, and there's some expansion coefficients S, then you haven't done anything if you replace the YLM spherical harmonics with the Slepian functions, the magenta G's here, because if you take them all, they're still L+1 squared terms, and you have an equality of expansion in either basis, because remember, they're just combinations of one another. But if your signal is regional in nature, like it's really just Greenland, because the first n functions that are made for Greenland are so well localized to Greenland, and the other ones are so poorly localized to Greenland, then you can approximate the signal by just summing the first n of them. And so for approximation of regional signals, that means that the mean squared reconstruction error, if there's no noise and no complications here, is really just the level at which you truncate, is the neglected eigenvalues times the signal that you're neglecting, but the eigenvalues are so tiny that you're having a very, very good approximation here. And so that's very, very useful. So I'll show that with an application to a geomagnetic anomaly here. Here, I'm showing you the standard spherical harmonics, and they're on the entire sphere, but I'm just cutting out the square that involves Africa. And I'm looking at a circle that involves a piece of Africa that I want to look at. And so here you recognize the orders and degrees of the spherical harmonics. They have these zonal and tesseral and sectoral patterns, and all together they're a complete basis for signals on the entire surface of a sphere. So if I try to show you here on the left is a magnetic field of the Earth, a magnetic field model to a certain degree. And it's for the whole Earth, but I'm looking at the circle in Africa here on the left. And on the right is all the spherical harmonics that are necessary to make the map on the left. And those of you in geomagnetics will recognize that the triangle that I cut out here is just not showing the Earth's main field, which is the big dipole that we all know. So here, this is the lithospheric magnetic field. And so 5,000 numbers are required to get us this map, including the area of interest. However, if I try to find a spherical harmonic expansion that just picks out this massive anomaly in the Central African Republic, I believe, centered around the city of Bangui, then I still need about 5,000 numbers here to show or to make this anomaly. And so here on the right, I'm showing all the spherical harmonic coefficients, which when expanded, give me just this anomaly and nothing outside. And so working in a global spherical harmonic basis to look at local structure is a really poor choice because you need a lot of numbers, most of which provide cancellation for the area outside. But so now let's do this in these Slepian functions. If you calculate them, I'll skip over this here. That's a calculation method, but this is what comes out. These are just Slepian functions for that anomaly in Africa. And you'll see I've again ordered them in the customary way. You've already seen them, but now I put them where they belong. And I'll try to expand that Central African anomaly in those functions. And so this is what you get. You get the right thing in spatial space, and you accomplish that with a really, really small set of these new functions. So in this case on the right here, about 100 functions do all the job of talking about the anomaly with almost no error inside of that region. And so the reduction from 5,000 numbers to 10 numbers that really matter is because in this space, the area of that circle compared to the globe is that factor of 50. So local bases, custom constructed for specific local areas, are really handy to approximate signals and then by extension to invert for them, as I'll show you in a minute. And so that is generally fitting with this notion of sparsity here. If you have a signal that's sparse in some basis, then you generally will gain by finding that basis and working with it. Now, as we were doing this and getting involved in geomagnetics, we also realized how closely these functions, when you look at them on the top here, how close they look to earthquake focal mechanisms. So obviously it's not a coincidence given how earthquakes work, point source earthquakes, and how spherical harmonics work. But just look at the fact that these functions look like moment tensors. So as soon as we had that, we realized that maybe in order to find signals generated by earthquakes and measured by satellites, like co-seismic gravitational perturbations, we will really gain by trying to look for these things in that basis. So the first example, and only one that I'll show you, is related to that large earthquake that happened in the Sumatra Andaman earthquakes. So what you're seeing here now is a prediction. It's a normal mode summation prediction of the geopotential, so the gravitational potential perturbation due to particular end member moment tensors, as you can see here on the top here, where I filled the moment tensors with ones and zeros. And so the different components that all together make up a full moment tensor, when expressed in the gravity field, look like this. And of course, they look just like these functions. So what we then started doing is looking at the time variable gravity signature as recovered by Grace. And in this slide here, I'm showing you all that happens when, instead of using spherical harmonics to expand the gravitational potential, you're using these Slepian functions. And I'm only showing you 3 Slepian functions. At the top, 1, 2, 3. I'm not showing you the zonal pattern. I'm just showing the ones that are bilobe. So sorry, there's the top left and the bottom right, that's the complement. And then I show 2 successive rotations. And so what you want to see here is the blue dots are the geode anomaly. This is a tiny, tiny perturbation of the gravity field due to a point source moment tensor earthquake. And those are the things that are actually recorded by the Grace satellites. And so in just 2 functions, and when properly oriented, you are capturing the co-seismic jump here that is caused, in other words, by this earthquake. So it's really one function and an orientation that really tells you most about this earthquake because it is a particular type of a megathrust earthquake. So take a look at the right here. The top function is perpendicular to the strike, and there is nothing going on in the gravity field. So of course you could use that to get an idea of signal to noise. And the bottom right function is the Slepian function that is most aligned with the strike of the Sumatra-Andaman fault, and that is where the jump is. So this opened a new analysis technique to look at time variable gravity and to find the expression of large earthquakes, because you can simply project them into a basis that is appropriate for where the earthquake is, and you can also use it to look for where the earthquake is, and you can pick out here, like this jump, what the co-seismic perturbation is, and that helps us learn more about earthquakes than we can from just seismometry. Obviously, we have information about moment tensor from seismic sensors, but they are not available everywhere. They are not always homogeneously distributed around the earthquake. And so the addition of gravitational potential perturbation, time variation information, such as is afforded by the GRACE satellite, really helped us in a couple of other papers that we wrote about different earthquakes, add the information from the gravity field, which is typically not measured or measurable. And that helps us constrain mechanisms of earthquakes, magnitudes of displacements, orientations, and so on. So they have become a tool of seismology. The gravity field has become a tool. Satellite gravity field has become a tool for seismology of large earthquakes. And again, that is literally just by making these functions and doing a multiplication, and the signal jumps out. So that is just sort of the start of properly solving geophysical inverse problems. So here is a picture of the GRACE satellite, which gives us time variable gravity. So I'll talk a little bit more now about specifically how we solve proper inverse problems. And it applies to both geophysics and also cosmology, which I'll touch upon very, very briefly. And the only thing about cosmology that's similar to geophysics or geodesy is that it's also looking at a sphere, except it's not from the outside in, it's from the inside out. So what are those common problems, and what are the types of problems we solve? Well, look, the data that we collect is either limited to this region R, or it's unavailable outside of the region. So inside R, we're going to have some manifestation of some geophysical signal, and there's going to be some noise. We do make some assumptions about the noise, and because we're treating many of these problems completely statistically, so let's just say the noise here is a zero mean process that is uncorrelated with the signal. And we're going to try and make some stipulations about the noise covariance. And so this is really the problem. This is what we have. We have noisy and incomplete data on the sphere. If I fill in the equations, this is what we start from. The data on the left here, D, is given by a signal, S, and a noise term, N, and that's available in the region, and it's unknown or undesired outside of the region. The zero mean is the expectation of the noise is zero, and we assume that the signal is uncorrelated with the noise, and so their cross expectation is zero. And we're going to model or assume certain things about the noise covariance, in other words, how the noise relates to itself, which in the case of the GRACE satellites was a big deal because that data is very noisy. How noisy? Well, here's an example. I showed you that I was able to pick out the Sumatra earthquake. If you look at the month before and one GRACE solution, it looks like this. And the month after, it looks like that. Your eye would never do it. Just cutting it out will never do it. There is so much going on in these GRACE data. The first thing you probably see is the stripes, which is due to orbital alignments, and then some speckle in region, which contains all sorts of signals. But in the region of interest of Sumatra Andaman, you're just not seeing it. So that's what I mean by noisy. Structured noise. Incomplete, well, the telltale example for the cosmology is that you look at the sky and you measure the temperature, and then if you're looking at the bright galactic plane here, this red band here, then you really cannot do anything with that, and your temptation is to just cut it out. So that's what I mean by incomplete, in addition to you might just want to look at Greenland or a spherical cap or some region of an earthquake. So here now are the linear and the quadratic problems. In both cases, we're going to try to work with a signal that we think exists, geophysics or cosmology or what have you, and it'll be some spherical harmonic expansion because it lives on a sphere and it's a complete expansion to infinity. The trick, of course, is, or the question is that we want to, in the first problem, find what SLM is. We want to find what the unknown expansion coefficients are of the signal. And so that problem is stated as follows. If you have these data and you have some knowledge of the noise, which you need to make, then you need to find a signal. And you need to, in other words, find expansion coefficients, but you can never do all of them. And so your estimate is always band limited to this L, which is less strictly than infinity. And that's the problem of inverting for signal from that type of data. Find the set of expansion coefficients and know how well you do, and know how well, know the effects of what you're doing, and know what you're missing, and all of sort of that statistical baggage. And then the quadratic problem is, given the same type of data and given the same knowledge of the noise, model the power spectral density of the signal. So we make a world in which these coefficients are drawn from a distribution that is zero mean, and whose covariance, which is the spectral density, we want to know. This is an example of an isotropic spectral density for convenience here. So the problem one is to find a signal from data, and problem two, the quadratic problem, is to find the spectral density of the signal from the data. Those are not the same problems, and they're not the same solutions. So in summary, all of our data are noisy and they're incomplete. A linear problem is to try to find the signal that gives rise to the data noisily observed. And problem two is find the power spectral density so that we can think about location of sources and cascades of energy, and generally know something about their spectral density, which is useful in many, many applications. So finding the signal, if you try to do a data match when the data are only available to R, then the best you can do is this here. So SLM hat is the least squares estimate of a set of band-limited spherical harmonic coefficients for an unknown signal. It is linear in the data. It involves integrating the data against the spherical harmonic over the region that you have. But you do have this term here. The least squares estimate involves, whether you want it or not, the inverse of that D operator that we've already been looking at. So immediately you want to recognize this as a sort of a, if D equals Gm, this is G transpose G inverse times G transpose D, if you're speaking the language of linear inverse problems in these symbols here, because D, again, is the inner product of all the spherical harmonics over the region, and then this is the available data. And so that's a linear operator in the data. But I told you that finding the inverse of this is really hard, but all of you would, in such a case, diagonalize that operator if you had it available and work in the eigenfunction basis. And that's exactly what the Slepian functions are. If you're solving an inverse problem and you have a dependence on a matrix that you need to invert, then instead of damping the solution, you can truncate it like an SVD, a singular value decomposition. And so that's exactly what the Slepian functions are. They are, in the continuous case, the singular vectors of this type of an inverse problem. And so then the problem becomes reconstruct a signal from a finite set of these Slepian functions, and instead of finding all of the SLMs, many of which you could never do. You're just asking for a truncated set of them, which you know are going to do a good job in approximating or inverting or yielding the inverse solution for a regionally observed or a regionally interesting signal. So like in any SVD, right, this is again a linear operator. It's d times g of the function integrated over the region. So it's the data times the basis function. And the dependence on the eigenvalue is explicit here. And since the lambdas get to be so small, you cannot invert them when they're nearly zero, but you just truncate them. And so instead of damping a giant spherical harmonic solution set and trying to find the spherical harmonics of an unknown signal, you are pre-computing the basis in which you know ahead of time that the signal will be sparse, and you'll compute the contributions in those bases by a truncated expansion, which you can truncate at will. Now, we did a lot of work of finding truncation and looking at signal-to-noise models, but in a nutshell, that's really all that it is. Problem 2 is quite a bit harder to fully characterize. And the key notion here is that if you ignore the fact that, well, if you ignore any of this baggage and you're saying, well, look, I'm just going to produce a power spectral density that will be the spherical harmonic product here over the region, squared because you're looking for power, summed over the orders m because you're assuming anisotropy, and then weighted by the number of values. This would be like using a boxcar window to do a finite interval spectral analysis. If you work out, as we did, what the distribution is of this estimator and how it relates to the truth, you will know that it is really, really bad. This is not news. This was known at least since 1898 when Schuster did this and said, you should never do this. This statistically doesn't behave properly at all. Now, again, we understand the statistics, and it turns out that the mean square error of doing this is dependent again on our famous D and a sum over the orders of the D square. It's an ugly thing to calculate, but the message is that a boxcar, a hard cutout of the signal of interest, and then trying to do this spectrum by just Fourier transforming this or spherically harmonic transforming this is really not a good estimator. So that's the second way in which we use the Slepian functions, not for expansion, but now what we're going to do is we're going to take the data and we're going to use them as windows. And so here these magenta functions will window the data. They will then transform it. I make the integral over the entire sphere because the functions have a complete support. But since I made the G's for a particular region, I know that this integral is regionally selective. Then I sum and square and weight. And that is what we call the multitaper estimate, which I'm hoping is at least familiar to some of you in the time domain, where it's a very, very popular method of doing spectral analysis for the exact same reason. And that's really what we have been doing, is we have been porting the mechanisms of the 50s and 60s for time series analysis onto the surface of a sphere. So I have one slide on what makes this quadratic. Obviously, you see the square, so that's quadratic, but I'm going to skip over this here. There were very many other methods that people looked at. Now, it turns out they're all the same class. And so I'll just go quickly over this without discussing it. It's on the record anyway, that if you do what we are doing here, a weighted multitaper estimate. So again, take the data, multiply by the spherical harmonic, multiply by the custom designed Slepian function, integrate over the sphere, square, sum, weight. Then what we show in our papers is that the bias, the variance, the mean square error of that sort of an estimate is much, much better than any other method that you could do. And yet it all fits in the same framework. You can pre-compute many of the things, and you can just multiply on the left and on the right the data, and you have a definition of a quadratic estimator. So that's what this multi-taper method on the sphere is doing. It returns intentionally slightly biased estimate by pre-making a Slepian function for a region, giving that an as small as possible bandwidth. And then you can show that your estimate is on average close to the truth within that small bandwidth and has a variance that is much lower than anything else you could do. And again, the whole control is in this Shannon number. It all really depends on the band limit, or the bandwidth of the estimator, and the area over space in which you have any data. And that's why that number is so important. So this number dictates the bias. And also, you, if you have that many different ways of windowing or tapering the data, it leads to the reduction of variance. And that's a long, long story in a paper that I think very few people have actually read, but we have worked out the covariance matrix of these estimators, and you show that, well, it's really almost diagonal up to the point n. And so if you take n tapers, multiply the data, Fourier transform, square, and average, then you get a reduction of the variance that is almost like they were independent estimates, which they are not, but they're approximately very uncorrelated. So I'll just show you an example here of this trade-off here now, because I said, well, you want to design a custom window, and for spectral analysis, you want to keep the bandwidth low. So here, this is different cases of L. L is 10, L is 20, 30, and so on. This is an example for cosmology where it's a double cap that you want to look at. So we have cut out the galactic plane. In every case, the black line is the target spectrum, so call that the truth. In every case, the gray band is the noise, which has to do with the detector. And then as you see the panels evolve here for different chosen bandwidths of the estimator, you are just coupling the spectral power over a smaller or larger bandwidth. So if L equals 40, then you really get uncorrelated estimators only every 80 degree. But as you're also seeing, the more you introduce this bias, the more you reduce the variance. This is the error bar. And that is really all contained in that Shannon number control. So if you have a global data set that you're interested in a region of, or you have a regional data set because you don't have information outside, what you really should be doing is find the smallest bandwidth that you can cover in this Slepian sense for that region, and then use that as data windows, and then simply transform, and that will be your best estimate. None of this requires matrix inversion. None of this requires iteration, and that's why this method is so popular in time series, but also now so competitive for spherical processes. I'll just show you an example again. So our application of this is if you look at our magnetic field, here is another rendition of the lithospheric magnetic field. It's a little smoother, this one. So you look at the globe, and this is what is non-dynamically generated, right? So this is the remnant field. And your eye sees immediately that the continents and the oceans have a different spectral signature. And you just want to know what those two things are. Then if you're doing this analysis and you just look at the continents, this is a partial expansion in Slepian functions, or you just look at the oceans, then using this sort of framework, you are able to confidently, and with the appropriate characterization of all the statistical structure, pick out what the power spectral density is for these things. So that's illustrated in this figure here. The top is the power spectrum of the lithospheric magnetic field when you look at everything. And again, the active field is nulled out here. We're not interested in that. If you're looking at the spectral density for just the continents, you see quite a different structure. And if you're looking at just the oceans, you look again at quite a different structure. So that's the mathematics of it and the statistics of it. Of course, the geophysics involves breaking this down to even smaller patches, making inference of why the spectrum has certain shapes, doing geological modeling of sources and all sorts of things. But the essence is here that the global spectrum is made up of pieces. And to get the local spectrum, you really shouldn't just cut it out and transform it, but you rather taper the edges with Slepian functions with a small bandwidth such that you get confident, robust, and efficient estimators of the sometimes very different nature of how the spectrum manifests itself when it's not all the same everywhere. And that we've taken to Mars and done other things with. So now in the fourth application, I'm going to return briefly to time variable gravity and sketch how we've used these inverse methods of linear inversion, this problem 1, to learn something about not earthquakes as my first example, but about the decay of the geopotential due to the melting of ice. So that's a paper in which we describe that first we really look at the noise. I told you have to make assumptions about the noise, which in practice means you have to try things and then often iterate. You got to then design a set of functions for the region of interest. And that was the Greenland case that I'm about to cover. So you've already seen those functions. And you know they're optimal for this type because they're the result of an optimization. You may not necessarily know what the bandwidth is of interest because, you know, it depends on your signal to noise and it depends on your field of interest and so on. So in practice, we also play with that and we make it a free parameter that we try to find the best for our purpose. But again, the central philosophy is that that global signal, which is regionally important, has a regional signal to noise that's much higher than the global signal to noise. And if you just use that new basis to work in it, then you can get really good estimates of what's going on. So that was, at the time that we were doing it, that was very, very different from what anyone else was doing. But it really was exactly the same what the old guys like Slepian, Shannon, and Wiener would have totally recognized in the 50s, except, and this is part of our contribution, is that they hadn't worked it out for the spherical case. And since we did, we could do it. So in one slide, that's what happened a number of years ago when we started looking, and we've done some follow-up to try to reconstruct the mass loss of Greenland and later Antarctica and Tibet and other places. And here in one slide, here's a decade of mass loss of Greenland. On the left is a map of a Slepian function derived estimate of how the surface density, apparent density, is changing, presumably due to the melting of ice. And on the right is the mass integrated over the area and how it inexorably goes down. The black line shows you the seasonality. There are gains and losses. The gray error bars are estimates. The blue line is the trend. And so with this framework, we are not only able to do the thing on the right, which is the overall mass loss, but since these Slepian functions have spatial selectivity, we're also able to identify where the mass loss occurs, what areas have mass gain, such as the central portion here. And all of that is still done using spherical harmonics, except we have recombined them by optimization into this local basis that is appropriate for Greenland. And then later on, we've done that for Antarctica and other places. So finally, and I'm going to watch my time here. I think I do have a few minutes here. I showed you 1D Slepian functions. I showed you some 2D Slepian functions. I showed you 2D spherical Slepian functions. Once we had the sort of the taste for it, the step up were vectorial Slepian functions. There now are tensorial Slepian functions. I'm going to show you one last example, which is relevant for geophysics here, and that is when you try to estimate the magnetic field from satellites. So here's my cocktail napkin drawing here. In the center is the satellite, is at a variable altitude, but let's say it's mostly at the orbit r sub s for the satellite. And what it is feeling is a combination of an external contributor, an interstellar or interplanetary magnetic field, that's W, and a field of an internal source, which is the potential V. And so the area of interest is again R. Here's a core mantle boundary, the inner core boundary, if you will. And so the problem is that we're trying to figure out what the field is of the Earth in those places of interest, while we're observing it from a satellite altitude, while it's being contaminated by external field, and while all of them are contaminated by noise sources. And that again is something that people have been doing for a long time for the globe, using spherical harmonics, where orthogonality and cancellation really help you. But when you are trying to do this just for a surface area of interest, a little region R, then none of this is possible using spherical harmonics. Everything interacts. You need many, many coefficients. The inversion is really horrid. Whereas by constructing a custom basis of Slepian functions, you have really good behavior. I'm going to do what I did before. I'm going to go slightly faster, but I'll give you the taste of it. And so 17 here is the observation equation. Is we know that we're at some point RR, so at some radius R on the unit sphere, but then extended. And we know that we have the contribution of two potentials, an external field W and an internal field V. And so this is the Laplacian of those two things vanishes. So we're looking for harmonic fields, which means we're not looking for time dependence. We're not looking for currents. We're really just sort of doing a baseline estimation of what's going on in, let's say, the terrestrial lithosphere or the Martian lithosphere. And the expansion of the potential is again just a spherical harmonic potential expansion. So the coefficients here are V, and YLM is just the same spherical harmonics. But now, because you're at satellite altitude, you finally have something interesting going on. It's no longer an approximation problem of observing something over a patch and trying to find a field. You're actually observing it at a distance. And so that distance gives you another operator, not just the spatial localization to some region, but also the fact that you're moving out in space and you have a degree dependent decay that depends on how far you're observing with your satellite. And that term that I highlight here, R over the planetary radius, is where you're at. And there is the decay. And so that is something that I'll be calling A later. And the W field is some other field, and both are unknown. And the objective is to find V and W so that we can separate them. And so we can study the Earth from these noisy and inner outer field contaminated observations. So I'm going to do this quickly here, but the apparatus we need are vector spherical harmonics. And I'm just going to show you some pictures here. The YLMs make radial vectors, they make tangential vectors, they make other tangential vectors. And so the basis, it grows quite a bit. And so where our initial scalar D matrix was an integral over the region of YLM times YLM prime, now you will see coming that we have regional integrals of P and P and P and B and C and B and so on. And so we work out all these interaction terms and we construct a proper basis for it. So we don't work directly in the vector spherical harmonic basis because we have harmonic fields. Turns out that when we have harmonic fields, then we can recombine them in the following way. This you already know. Inner harmonics and outer harmonics are for V and W. And what we do here is standard operation procedure, but we make new combinations of these harmonics, of these vector harmonics, and they're called E and F, and they are just what you need to express harmonic potentials that are due to internal or external sources. So the localization hasn't happened yet. But now we write the field B, this is the magnetic field vector, as the gradient of the potential and the gradient of the outer potential. And because we combine the vector harmonics into the gradient vector harmonics E and F, what you want to see here is that now the gradient can also just be up and downward continued. So this is a technicality that is geophysical in nature and has nothing to do with the localization yet, but it is just saying that you will have an inner and outer field. They are both potentials. You will need vector harmonics, but not all of them. So you combine them in such a way that if you have found these coefficients V and W, which I've been trying to find, then you know them at any other altitude. And of course, the object is to reconstruct these unknown coefficients from their observations at that altitude. And so you see that you will have to undo the effect of moving up or down in space by inverting these A operators. And so that's the restatement of the problem, right? The data are available at an altitude, only in a region. They're going to be gradient vectors of an internal and an external nature. There will be noise. And when it's not in a region, you don't care or you don't want to know. And so that's the statement of this problem, is to obtain from discrete satellite data collected within some confined region, but at a varying altitude above some surface, noisily observed, contaminated by inner and external fields, and you only want to know the inner field to find the coefficients in some band limited set. So the solution, again, is using Slepian functions, but now they're custom constructed, not only for a region, not only for a band limit, but also for an altitude and for the inner and the outer field. And again, these papers that we wrote are rather horrendous because it's just, you got to keep track of all the indices, and the notation requires 3 tables and so on. But the essence is hopefully clear, is we collect these coefficients in vectors, we clean up some housekeeping of these, stick all the basis functions and all the unknowns in vectors and matrices, and then try to solve it. So I'm just not going to read this other than saying we have a new notation. It's very convenient. It's also rather ugly. You write out the problem again, and then you're looking for a least square solution. What you want to see here is that you have the data. You want to find these unknown coefficients. They have 2 contributions. You only know it in the area, and you want to minimize the least squares formulation of matching the data in the region. And the solution needs to be the field due to external and internal sources. So when you write it, the Slepian problem, which used to be a simple scalar, matrix vector multiplication, now becomes a matrix multiplication. But once again, you're just diagonalizing in this new space, and you're just getting new Slepian functions. They are now vectorial in nature. They now know about altitude, and they now know about being inner or outer. So here's some examples for North America. These are the best internal field only gradient vector Slepian harmonics. These are the the very best. This is the 100th best, still very good, but completely different in nature. This is the best full set when you're combining both inner and outer fields. This is the 100th or 500th best. I'll pause here for a second at the best full field gradient vector Slepian function. So it knows about North America as the region. It knows about 2 band limits because the internal field might have a different band limit than the external field. And it knows about where the satellite is. And when you know all these geometric things, you could just solve for the Slepian functions, and that'll be the basis to invert for your field of interest. So the Slepian problem, slightly extended, a lot more notation, but it's really just, again, that same system. You have, in this case, a linear inverse problem. You're finding a new basis, and you keep track of what goes where. So in conclusion, I'll just show you a few of the things that we've done with it. Mars, the Martian magnetic field, is highly localized. This is a picture of Mars. There is the crustal dichotomy. You're all seeing a region of interest defined as, well, what is going on there? And what we have done with constructing these custom Slepian functions is we've tried to make new models for those regions from primary observations. And the reason is that we have global models for the Martian field, but they're made with global data. But we also have a lot of data that were too good for the global model. They were coming from low orbit satellites where you're close to the source, so that downward continuation is much less severe. They were taken at night where there was less noise. And so what Alain Plattner did here is he selected a set of low altitude nighttime observations, vector observations of the magnetic field in order to study this particular region of interest, which I'm showing here. And with that framework, we made local models, and the colors are coming out very badly in the next two slides. But what you want to see is a view of that southern polar cap. And on the left is our solution for the magnetic field, a radial field component only, evaluated at the surface. On the right is what it looks like. On the right is essentially the same thing, but accomplished a slightly different way. The second thing here is on the left is again the model that we were making, but now we're superimposing satellite tracks to show you in a minute how it fits the data. On the right is the same model, but evaluated at different altitude to get a different view. And here are direct comparisons of what the satellite is seeing. Now there is much detail here. The columns are tracks, 6, 5, 4, 3, 2, 1. The rows are components, radial, colatitudinal, longitudinal. And what you want to see is that where the fit is very good because the lines go through the error bars, that's what we are doing, using altitude cognizant inner-outer Slepian function analysis. And the lines that don't go through the data, dashed lines, are when you're trying this using local functions, using global functions. So that's an illustration of a post-factum look at how you actually fit the data. Does this work? Because otherwise you'll always get a model, but here we're taking the model data back to the prediction of does it fit the data, and we're comparing it to those other models. And again, the essence is that when you have regional data that is so good that in a least squares inversion for the global field, it just gets washed out, then you should be doing a local inversion. And if you do the local inversion in a custom-made basis that is appropriate for the problem, then you get a good model that fits the data well, and then you can do the geology with it, which is what I'm not going to discuss here. Errors, I'll skip over it. So 2 slides on what this is all about. Linear inverse problems, right? In the highfalutin view event, these are inverse problems, or these are approximation problems that have linear operators, compact operators between Hilbert spaces, between function spaces that are square integrable functions, in which these blue kernels that I started with are reproducing kernels. And if you write these things globally, then you have an idea already of what a singular value decomposition is, because it's just a spherical harmonics, and you know how they up and downward continue, and you know all about it. That's what we have known. But none of that framework applied to regional data, but it does apply in a new basis. And that's the Slepian functions. They're a new basis for those sorts of problems when they're of regional interest. And I've shown you how to make them, and I've shown you that if the regions are very symmetric, it's actually really easy. But in any of it, it always begins by an acknowledgement of what the problem is, and a diagonalization, an algebraic eigenvalue problem that just gives you a new basis, which itself is a linear combination of the old basis. And so it's almost amounts to sticking another matrix inside your normal operational framework, and you can do the geological, geophysical, and statistical analysis. So that's a one-page summary of the linear problem. Last thing that came up here is instead, again, of doing a damped inversion in a large basis that's no good for the region, we do truncated inversions in new bases that are custom made for the region. Then the summary on this quadratic estimation is, well, this whole multi-taper method, right? You make smooth and biased, intentionally biased, but over a small bandwidth estimates of the spectrum. You do this by multiplying the data with a set of custom-made windows. Because you have multiple windows, you have multiple ways of estimating the spectrum. You could average it. Because the correlation tend to almost vanish, you get a variance reduction. And the whole control is in how much of your data you have observed, as in encapsulated by that Shannon number. So Slepian functions, they're spectrally and spatially concentrated functions. They're doubly orthogonal bases on the sphere, and both on the whole sphere and on the portion that you've selected. They are an ideal basis to separate signal from noise and to do regional things. If you use them as a data window, they're an ideal way of solving spectral analysis problems. And that's really it. That's the full story of Slepian and how it applies to geophysics when it's for real data observed at altitude, sometimes vectorial in nature, over regions of interest, both in magnetics, gravity, or any other application.
Thank you very much, Frederick. It's an exciting talk. I would tell that I never looked at this Slepian functions, but you opened for me, it's a new world, and I have to look there. it's exciting. Thank you very much, and I hope we will have some questions specifically directed to the presentation. Please, raise your hand or just the open microphone, not simultaneously, probably. Okay, Malcolm, please.
Thanks. Great talk, Frederick. I very much enjoyed it. Beautiful talk. I just wanted to have a speculative question. So you showed very nicely how one can build Slepian functions to concentrate on a region and have all of the advantages of global basis, but concentrated in a region, and you applied them to data analysis and inference problems. Is there potential to, or has anyone looked at this in terms of numerical modeling of spectral methods for solving different seismic or other types of problems which are normally applied to global basis functions, where, let's say, the only interesting thing happening might be in a small region, or people who use that in the context of Slepian?
Yeah, there are some, but not very many. There's a handful of wave propagation problems and in optics, so no, there has not been very much work in forward numerical modeling, and maybe that's because all the other methods are ultimately doing really well, or there's a lot of compute power, and maybe there's too much, finicky analysis that needs to precede that. I'm aware of some, but not many, and so it's mostly for representation, inversion, and spectral estimation that I'm aware of.
But there's no fundamental barrier to considering them in that context.
No, I think, but I think let's talk about wave propagation. It's like wavelets, right? A completely other thing that I didn't talk about. There's some wavelet forward modeling, but it hasn't really taken off, right? No. Because, other methods like spectral element methods and so combine already the best of being able to grid it and still have a spectral representation. Right. Yes. And so I think it's largely for the same reason.
Okay, thanks. Great.
Ilya, please.
Yeah, thank you very much, Frederick. I'm just joining everyone to say that it was an exciting talk, very informative and very nicely presented. My question is the following. You definitely played a lot with this. What are the chances to generalize it to 3D? Imagine that we want to work not with surface of the Earth, but with entire Earth. Is it doable, or what do you think about it?
It's done and dusted. So my second slide on 2D Cartesian didn't reveal it, but what's behind it is the fact that this works in n dimensions in Cartesian. And in fact, the operator looks exactly the same. And so in the Cartesian case, we show what that is. And so in the interior of a box, it all looks the same. It all behaves the same. You just have to compute it. On the other hand, on the interior of a sphere, you have to do a little bit more work, because then you have to combine a spherical harmonic basis with a radial term, and there are multiple ways, like, you know, Bessel Fourier expansions and other things. There's various ways of doing non-harmonic expansions of the inside, and that's exactly what Volker Michel has been doing. So if you look at his papers on Slepian functions on the ball, they're doing exactly what you're saying. But, you know, we worked on the vectors on the inside and the outside, and you can see that stuff, it gets involved. And but that all has been done. And so indeed, look up Volker Michel's work on ball Slepian functions. And he's written at least 1 or 2 books actually on doing a lot of extensions on this thing.
Great. Yeah. Thank you.
Now I see also the hand of the Penliang, please, Penliang.
Hi, Fred. Really, thank you very much and congratulations. And my first question is basically you try to say the harmonics expansion is good for global application, but for localized application, we should use the Slepian basis. Then in this case, we know basically also weblet could also be used for localized application. And
yes,
I see you have some cooperation with Volker
yeah.
Media. In this case, do you both try to see the difference between Slepian basis and weblet basis?
Yes, that's an excellent question. And so what I've tried to hammer down here is that Slepian means deciding ahead of time where your area of interest is. Take a bandwidth. It doesn't have to be bandwidth. It could be any portion of the spectral domain, and take a portion of the spatial domain. And then you have a basis for that. And then we worked out all the statistics of what you do when you're stuck with that region. And that all is very different from a wavelet basis, where the wavelets are going to trade off the spatial domain over which they extract information with the wavelength of which they're able to extract that information. And the statistics are completely different, because you will extract local information from small wavelets and larger information from different wavelets. And so they're not mixing the same. So if you're looking at something geologically motivated, where you know where you're looking, or you have data in a region, the Slepian approach is the most natural one. If you're looking for what's important and you're able to, you know, stretch and squeeze the way wavelets do, then the wavelet base is going to be the appropriate. And so that's, again, like you're saying, where Volker's work and Willy Vreden's work and so on is very relevant, because they work out what those types of wavelets are for those types of problems in a sort of spline way that they call, and in the whole framework of these reproducing kernel spaces. What they are not working out is the statistics of it, because I think it would be fairly horrible. So because wavelets scale and squeeze with their different resolution, I haven't seen any detailed work on the statistics of their coefficients. And because the Slepian functions is a basis, and once and for all you're stuck with it in the region, we are able to work out on what the statistical distributions are. So it's complementary. It's not one size fits all. I've worked on wavelets and I'm interested in it, but the central part of Slepian is that you pre-decide where you will be looking.
Yeah, it was trying to say they are complementary. Is it possible to think about the combination of both?
Yes, that is also possible. And that is something that also Volker has done, because he has given up orthogonality and made redundant bases and made frames where he will combine spherical harmonics with Slepian functions, with radial basis functions, with all sorts of things. And so there is a lot of work in that area where combined bases are being made. But again, the emphasis there is on approximation and reconstruction of field, and not so much on the statistics of spectral estimation or on linear inference problems.
And Dr. Lee, sorry, one more quick question to Fred.
And by the way, sorry, Pei Liang, your work has been very influential, because I always keep referring to your papers on SVDs in Geodesy. And so that's really the limit case, right? The continuous case where if you have continuous data, then the Slepians are the exact SVD of these problems. But now we're able to do it for weird regions and discrete sets.
Fred, I could see you try to estimate also one for linear inversion, then the other is for power spectral. This will be the quadratic estimation. And Fred, you know, let's say if we have a measurement, let's say y, and then in order to estimate this power spectral, then my impression you will need something like y square, right?
So
this is the quadratic quantity.
Let me show you one thing to see if I understand you right. I'll show you what I meant here in this paper that we wrote about the spectral estimation problem in 2008. And so here's Tony. At the very end, the only thing you have to read is the beginning and the end. At the end, this is the summary. And it says, all of these estimators look the same. They're making an estimate that combines the data on the left and the data on the right, and you need to make this operator Z. Once you do that, you characterize the covariance of all these things and so on.
Oh, yeah.
And so the whole sphere estimator is the easiest one. That's basically just a spherical harmonics. And the maximum likelihood, which was popular in cosmology, involves an inverse, doesn't work without iteration, but it's still a quadratic estimator. And so the multitaper, and we never actually do it this way, but what it allows you to do is it allows you to compute this G here, which is the inner of the quadratic form, that you compute once for your band limit, for your bandwidth, and for your region. And this G is, so look at this one. So you make this Z out of this G, and then all you need to do is 181. The only trouble that people aren't doing it this way is that the expression is so complicated, but it really shouldn't stop anyone. 134 it's actually, sorry, no, that's not why people are not doing it, but here's the precise form. So the 134 is what you need to stick on the inside and then left and right multiply. And so what I want people to do is to pre-compute data grids like you would do in astronomy or cosmology or geomagnetics, and then pre-compute these G matrices for regions of interest, and then store them, and then the spectral estimates will just be the quadratic form obtained by left and right multiplying the data on a pixel basis. So that's just like the linear estimate is just some linear operator times the data. The quadratic estimator is D times some other operator times D. And we worked out what that operator is and what the statistics are when you do that. Does that go towards your question?
Yeah, thank you very much, Fred.
Sang-Mook, I see you hand is raising.
Yes, it's more of a comment that if you had been in Korea, you would have heard, be aware of the local news here that yesterday the main local news was that Korea succeeded in launching 1.5 ton satellite on a Korean-built rocket, 7th in the world. And so I think it's timely that Frederick's talk is comes at a time when Korea is now going into space, and I'm sure there are many students here listening your talk and will be very inspired by it.
That's good news.
Comment.
Because more satellites is better, and we need to keep observing our Earth for sure, more so I think than other planets potentially, and I'm glad that's the case.
Yeah, that was yesterday's headline. Yeah.
I don't see any more hands. I guess that it's the questions. It's going down because of the people. It's tired. But I would like to mention one thing. It's important because it's a Keilis-Borok medal. When Keilis-Borok established the series of the conference, he told once that it's a please never stop speaker, never stop the questions which come in. Just we have to enjoy this, getting more and more information and more something to think about in our future. Frederick, today you gave us a lot for thinking. You gave us a lot of not only the perfect mathematical formulation of what can be done, and in very simple way, that's not everybody is doing this way. And it also gave us some broad the feeling as what we can do in our own field. For example, using the Slepian or using different forms of the spectral analysis. Thank you very much for the wonderful presentation. I thank also all your, the questions and the answers which you gave. And now I would like to just close the session and thank Frederick again. And definitely this crystal medal will go to you, but you have to choose the way how to get it.
Thank you very much.
Yeah,
thank you all for listening.
Thank you. Thank you very much. Enjoy your meeting.